let's continue our review of this excellent paper, Spacetime Algebra as a Powerful Tool for Electromagnetism. And we have made it, we started section 3.2. We started as far as the spacetime product, which is absolutely a very vital concept to this entire endeavor. The spacetime product is what makes the spacetime algebra a thing, right? Without a product, you don't have an algebra. And the spacetime product is the specific product that turns a geometric algebra into the spacetime algebra, right? It really defines the unique geometric algebra because the spacetime product demands a few things. First of all, it's talking about 4 dimensions. We got to talk about dimensions, by the way. And it also establishes the Minkowski metric, which is another thing we glossed over a little bit in the last lesson. So let's review a little bit of where we're standing, emphasize a few points, and then move into this critical subject of the spacetime product. So let's begin. We began our work, we will begin our work today right where we almost left off last time, which is these fundamental properties of the spacetime product. And there's a few things I want to emphasize about this. The first is when we're talking about A, B, and C, notice this very important point. A, B, and C, these vectors that we're using as exemplars for these axioms that establish the properties of the spacetime product, those vectors are in Minkowski space. They're in this vector space M13, this inner product space M13. Now, I've already said that the algebra that we seek, right, the geometric algebra, which I'm drawing here to be contained in this box, right, is we're going to specialize all of the geometric algebras to one particular algebra, the spacetime algebra. And through my explanations here, I am going to occasionally do some demonstrations of why that's the case. Basically, what I plan to do is from time to time drop into your regular 3-dimensional vector mathematics that we've all learned in high school and first year college, and talk about the geometric algebra associated with those vectors. But of course, the spacetime algebra is dealing with the notion of 4 vectors, right? 4 vectors of special relativity. So that's a 4-dimensional spacetime geometric algebra. And also, importantly, the metrics between these two are different. And we're going to talk about that in a moment. That's going to be we're headed right there to that subject right now. So the general idea is we're taking this geometric algebra, and it's really, we're going to focus on just the space-time algebra, right? And that first step of focusing on the space-time algebra is to acknowledge the fact that a big piece of this geometric algebra, remember, the geometric algebra, it is an algebra, but it's also a vector space, right? And the vector space contains vectors, and we kind of went through this last time, and some of those vectors are the same vectors that live in M13, which is, of course, the 4 vectors. And those 4 vectors we're calling for right now, or the paper's called ABC, right? ABC are exemplars of these 4 vectors that live in M13. So they don't do anything like, TX, which they could. I mean, that is a 4 vector, but they're saying, no, we're just going to call these things A, B, C, right? We're going to give them just straight up names. But part and parcel with this is those 4 vectors, if they're in this geometric algebra, they have to have a basis system, and we know what that basis system is. We call the basis system E0, E1, E2, and E3. That's our typical basis system of 4 vectors. However, we are going to change this notation, right? And that's because the paper will eventually change the notation. And it's very important and telling. And I think it's kind of exciting because this is an example of a notation change that kind of sparks the imagination. we're going to change this notation from E1, 2, 3 to E0 we're going to call gamma 0. E1 we're going to call gamma 1. E2 we're going to call gamma 2. And E3 we're going to call gamma 3. Now, if you've been following the lectures on prerequisites for QED, you'll immediately recognize that these are the same symbols that are used for the gamma matrices. However, and that's important. That's why we're doing this. We are doing this because, hey, don't those look like the gamma matrices? But the answer is no, they don't, because these are just the four basis vectors in M13 that specify a spanning set of orthogonal basis vectors. We'll talk about the orthogonality in a moment because that's critical. And we're just literally renaming them. So these are meant to be basis vectors exactly like this. This is a renaming. It's not even like it's literally just like changing the typography. Now, the reason we're doing this is because, yes, down the road, we're going to discover that the Dirac matrices of the Dirac notation, I'm sorry, not of the Dirac notation, of the Dirac equation, are indeed equivalent to or associated with the very basis vectors of the four vectors that live inside the spacetime algebra. And when you have a spacetime algebra, you can interpret these basis vectors of just this piece of it to be the Dirac matrices. And what we say is the Dirac matrices are a representation of the basis vectors, of the simple, straightforward basis vectors. But how much easier is it to think of four basis vectors than it is of these four bizarre Dirac matrices that really came to us through a very strange angle? Oops, I'm missing an E in spacetime. And so hopefully when we get there, you'll be like, wow, that's really, really fascinating. Okay, so we end up with these four vectors, but we also realized that we need to also augment the space with the real numbers. Now, when you do that, obviously the real numbers cannot be constructed out of these basis vectors, right? And so, but the real numbers is a vector space in itself. Remember, this here is the vectors. This is the vector space M13. This is another vector space that we're adding into our big vector space. So we're kind of putting these two vector spaces together. Now, the way you put two vector spaces together in the form that we plan is something called the direct sum. So we're not going to jump on that right now, but keep that in mind. But the real numbers have their own basis vector, and it's the unit, right? The number 1 is now the basis vector of this one-dimensional vector space that we've kind of added to build up this algebra. And unfortunately, well, not unfortunately, it's actually pretty interesting, we have other vector spaces that we need to also direct sum into this. And I think in the case of the space-time algebra, there should only be 2 more. This one, the first one we add, well, it should be 2 more or 3 more. Hold on. No, there should be 3 more. Then another one. So there's another one to add too. Let's see, I'll put that one here like this. You're supposed to think, okay, you're going to add these 2 together, and then you're going to add this one to it, you're going to add that one to it, you're going to add this one to it. So you should end up with 4 of these. And we'll be building each one of these as we need them. But what's important to understand is, remember, we're combining these vector spaces together, and each time we do it, each of these little subvector spaces are going to have their own basis vectors that are going to be added into this. This one only has 1 basis vector. It turns out this last one will also only have 1 basis vector. This one will have 4 basis vectors. Am I right about that? This one will have 4 basis vectors. Yeah. And this one will have 6. So you have 1 basis vector, 4, 6, 4, 1. And for those of you who've studied with me about differential forms and the exterior algebra and the exterior calculus, those numbers will sound really familiar. And I guess so we're consistent with the future, this really should be listed first, right? I should move this over here. Let me see if I can do that. Yeah, this is a better way to look at it, because you want this low dimension, dimension 1, dimension 4. This will be dimension 6, dimension 4, and then dimension 1 again. So you have this sort of symmetry, 1, 4, 6, 4, 1. But we'll see why that is later. We'll also understand exactly why these direct sums are here. These direct sums are really, really important. Direct sums is used to make bigger vector spaces from smaller vector spaces. But what's interesting, so the point of this, in a way, the point of getting down this little descriptive tangent of where we're headed, is to focus on this box right here. Because these 4 vectors, they're a bit of an anchor to the entire theory of geometric algebra. And it took me a while to figure this out, so I want to save you the trouble, right? I'll save you the trouble. Why don't I finish my words here today? And the point being that these vectors A, B, C, right? That's what this is talking about, right? When this assumptions are made about the geometric algebra, these properties that they lay down as fundamental and foundational to this theory, of which everything flows from these properties. The whole theory flows from these 4 properties. But these are not members of the geometric algebra in its entirety. They're only members of the little subpiece of the geometric algebra, M13. These are rules for 4 vectors. They're not rules for any of the other elements of the geometric algebra. Now, maybe at this point that seems a little obvious, but if you study the subject raw, you kind of have to come back and remember, wait a minute, this whole thing is really built on the properties of these guys, and knowing how we want these guys to work, we start realizing exactly what we need to add to the theory, and it all flows from this. And more in particular, when we talked about this one the last time, we realized, oh, this contraction axiom forced us to add the real numbers. We kind of went through that last time. And so that was the first implication of the power of this to expand our vector space of 4 vectors into something that looks like a geometric algebra. One thing I did not emphasize, although we stated it and it's very obvious right here, is the presence of the metric in this right here. And that's what's a really critical fact. And this is true for any geometric algebra, right? The fact that they wrote eta here, in our case, eta it represents the Minkowski metric, where you take 2 4 vectors and you jam it into the Minkowski metric and you get a number back that's either space-like, time-like, or space-like, time-like, or null, light-like. And I guess in the method that they're using, a negative number coming out of this process is a space-like vector, and a positive number is a time-like vector. But the point is this axiom right here, it's the core axiom at the foundation of the whole thing. And what do you see in the middle of it? Right there you see the metric, right? The metric, and I'm putting this in big old green, the metric is literally built in to this axiom of this space-time algebra. It's part of the fundamental premise of this algebra. And this metric could be very general, right? It could have been the case, right? It could easily have been the case that this metric, eta of a, or remember, it's a metric, so it could be eta of AB. It doesn't really matter. It could have been that this is the Euclidean metric, and it would be positive definite, right? So this could be, this could have been, so this equals epsilon magnitude of A squared, right? Where this magnitude of A is what the metric defines. Now, if it was Euclidean, then we wouldn't need the epsilon because it would always be positive. But because our metric is Minkowski, we include this epsilon so we can isolate the sign from the magnitude of the metric contraction, or the contraction between A and B. But what I'm trying to emphasize is that this metric is part of this 4-vector space, right? I'll put it here in green, the metric. And because it's the Minkowski metric, that's what makes a general geometric algebra the spacetime algebra. It's because of this, right? This metric is what takes this geometric algebra and turns it into the spacetime algebra. The two things, the fact that this is a 4-dimensional vector space and that it has a Minkowski metric. That is the two things. Those are the only two things you need to take your general geometric algebra and get a spacetime algebra. Because I could say, well, forget M13. I want, let's say, I want a 7-dimensional vector space, right? I want this to be 7 dimensionals, 7 dimensions, and my metric is going to be some weird 7-dimensional metric. That'd be fine. I would have E0, 1, 2, 3, and then I would have E4, E5, and E6, right? And I would have to add a few more vector spaces, it turns out, to make this whole thing complete. But I would have a 7-dimensional geometric algebra with a particular metric, and it would be a very unique, interesting geometric algebra. It just wouldn't represent anything in physics that we know about, or better be careful there, that I know about, right? So, but the one that we do know about is, hey, if you take this concept of this geometric algebra, which is just picking a vector space, and using these same axioms, no matter what geometric algebra you take, these axioms will always apply. I pick a vector space and I pick a metric, and I've got a particular geometric algebra. And when this vector space is M13 and when this metric is Minkowski, I have the spacetime algebra. And now we haven't gotten there yet. We haven't finished it. We won't fully finish the spacetime algebra until we know everything there is to know about these things. And there is a few other key principles we have to deal with, but that is the program here. That is the program. Okay, so the rest of today, we are going to leave this subject of these axioms because I think we've spoken about them plenty. Understanding that they apply only to the 4 vectors, right? Only to the 4 vectors of our geometric algebra, which is, I think, fascinating. That the product, remember, this product has to be good for that's an important point. The product that we're trying to create has to be good for everything in the geometric algebra, right? That means if I take anything out of this algebra, right, I go into here and I pull out something I call, I'll call it X, and X may be, I pull out something X, and then I pull out another thing Y. I have to be able to write the geometric product, or the space-time product, as we're going to call it, of X times Y. I have to be able to write that. And X times Y is going to have to equal Z, and Z's got to be inside the algebra. X and Y do not have to be from M13. X and Y can be from R, or it can be from this thing that we've yet to create, or this thing, or it can be the sum. Remember, because you're supposed to be able to add anything in here too. So I should be able to take something from here and add it to something from here, and that counts as X, right? And then Y could be something from here added to something here, and that counts as Y. I need to be able to take the geometric product of those two sums as well, right? So the geometric product is not forced into this little box. What is forced in this little box is the axioms that the geometric product must satisfy. So whatever this product is, we force it to satisfy certain rules for these guys, and then we accept whatever we're forced to accept for everything else. We accept whatever we need to expand the vector space M13 to create the overall space-time algebra, and then we accept whatever rules are forced upon us for these other geometric products of arbitrary members of the spacetime algebra. And that process is actually pretty tough. But we're leaving this sort of 4-vector set of axioms, and now we are moving on to something else. We're going to talk about the geometric product in a little more detail. And this paragraph here is the next paragraph of our study. And it's a doozy, right? It's a doozy. There's a lot to talk about inside this paragraph. And this paper, it really wants to get to the notion of electromagnetism very quickly. And so it offers this strange language with these new symbols, this dot and this wedge, which are familiar symbols to anybody who's dealt with a lot of vector analysis, and certainly, well, this is the forms and exterior calculus, exterior algebra. But this paper doesn't have the time to really dig into why these things are what they are, how they're proven, and we are going to spend that time. This is one of the gaps that we're going to fill. But this is all you really need to know. I mean, you could understand this formally and proceed through the paper, but we're going to spend some time here. And so we're realizing still a couple things. A and B are still members of M13, right? So we're still looking at these formulas. Whenever we see A and B, we're still stuck in M13, this little sub-piece of our ultimate final algebra. And again, we will build up the rest of the algebra from that. So let's start looking at first of all, let's just look at this thing, right? It's basically saying, well, it's literally saying that this space-time product between two vectors in M13 can be decomposed into two parts. The first part is this dot product thing, and the second part is this wedge product thing. And now we have to say, okay, well, all right, so what is he going for? What are we going for here? Well, this dot and wedge product are supposed to be familiar, right? They're saying, oh, this is easy. Don't worry about this geometric product, this space-time product, because it's really the sum of two things you already know about. You know about the dot product of two 4 vectors, right? That's easy because the dot product of two 4 vectors is just eta A, B. It's the Minkowski contraction of A against B, and that's a scalar. Now, that being a scalar is very familiar. This other part, a wedge B, is probably less familiar, but they're hoping that, oh no, you've studied the exterior calculus, so you probably even know what that is too. Now, the paper is very good about saying, well, a lot of our readers probably don't know about this, and then they talk about it here, and then they go through these geometric analyses later, which we will follow, right? We're going to follow this paper literally. But many people will find both of these pieces familiar. What a lot of people will have trouble with, if you do find both of these pieces familiar, what you might immediately have trouble with is saying, well, wait a minute, this is a scalar, and this is what's called a 2-vector. It's a directed area. How do you add scalars to 2 vectors, right? So that is something that people will scratch their heads about. And I'm not going to let that sit. I'm going to fill that gap for sure. But for right now, we are going to just understand that they're offering this up as a definition that they're going to have to explain these two things. And they kind of leave it up to the reader to dig in a lot on this. This is the essence of geometric algebra, and they're kind of saying, they don't have a lot of time in this paper to really build it up from total scratch. So they offer a reference, for example. But they do build up a lot. They build up these key points, and you could follow this paper by literally accepting these things. But we're going to focus on studying this paragraph a little bit more and focus. So right now we're going to focus on this part. And for the rest of this lesson, we're just going to focus on this, what I'm going to call the scalar part of this expression. And then in the next lesson, we'll either finish that up or focus on this, this two-vector part, this wedge product part. So we should just read what they say. We should read the literal words of the author, because the authors have thought a great deal about this. Decomposing the resulting associative vector product into symmetric and anti-symmetric parts produces the proper spacetime generalizations to the three-vector dot and cross products that we are seeking. So what they want to say is that they are trying to generalize the three-vector dot and cross products. Well, here's the dot product. So this must have something to do with the generalization of the cross product, I presume. And just to try my best to be clear, this spacetime product is not scalar. The only time it's scalar is when you're doing the spacetime product with a vector by itself, right? So if we had A, we would expect everything here to be scalar because of this axiom, right? So if we're dealing with AA, we're expecting AA to be the spacetime contraction, the Minkowski contraction of A with itself, which would mean A, based on this formula here, we would write AA equals A dot A plus A wedge B. But AA and A dot A by the axiom are the same thing, right? So this would have to be 0 for A dot A. So that's an important point, is to understand that this rule applies to any two vectors. We're going to have to learn why this piece is 0 a little bit later, but this contraction rule does not apply to AB. It only applies to A squared, A literally squared. So continuing, the symmetric part of the product, and then here they list out what they mean by that. So the symmetric part of the product, meaning this product here, this product has a symmetric part and an anti-symmetric part. And they want to say the symmetric part, which what they really mean is this part right here, right? This is the symmetric part of the product is this piece right here. That symmetric part of the product must equal A to AB, and it must equal this dot product. So that's a new concept, right? Right. The symmetric part of the product is not obvious from here, and it is a bit of a jump. So we have to understand the following kind of obvious formula. We write AB, the spacetime product of AB, clearly equals AB plus BA plus another copy of AB minus BA, right? And then divide the whole thing by 2, right? and the BAs cancel, the ABs double, but you divide by 2. So we've written this out in this very plain way. And then the idea is that this part here is the symmetric part, and this part here is the anti-symmetric part. And what they want us, so that's a very, now notice we've not introduced basis vectors here yet, right? All this talk we've got is without basis vectors. That's what we mean by coordinate free, right? These are all what we would call proper vectors in the sense that we have no coordinate frame. And this is probably our first example of a little bit of a demonstration that uses purely proper vectors, no basis vectors. We've just split, we can take any two vectors and just immediately break it up into a symmetric and anti-symmetric part. And what they want us to see is that, okay, this symmetric part has to be identified with this dot product, which, by the way, is commutative, commutes. So these two dot products. So that's what they want us to understand. So can we demonstrate that? Well, we got to go to the last sentence of the paragraph for our hint. The symmetric part of the product, which we've now identified, is precisely the scalar dot product inherited from the space-time structure of M13. So this is really a great statement. The space-time structure of M13 defines the symmetric part of the space-time product, which is the scalar dot product. And why is it inherited from that? Well, because you've got this eta. And that eta has the space-time structure built right into it, because what is space-time structure? Space-time structure is the metric. And when people study general relativity, it takes them a while to get their head around the idea that space-time is the metric, right, in general relativity. But it's also true in special relativity. The notion of space-time is completely wrapped up in the Minkowski metric. All of the Lorentz transformations, all of the rules about speed of light being as fast as you can go and no signaling and all of that great stuff, it's all about the metric. And they want to emphasize here, the authors, I feel, want to emphasize here that the space-time structure of M13 is automatically brought into the whole problem through this contraction axiom. So, but this is still just sort of a statement. The symmetric part of the product is precisely the scalar dot product inherited from the space-time structure of M3. The last equivalence follows from the contraction relation. So that's our hint on how to show this. The contraction relation, a plus b squared equals a to a plus b, a to a plus b, demanded by property 3.1d, which is, of course, the all-important contraction property, right? Property 3.1d is this guy right here. So let's unpack this and make sure we're very comfortable with this idea and then call it a lesson. Okay, so we're now going to look about see if we can understand how to take the space-time product of any two vectors that live in this portion of our geometric algebra, with the understanding that we still don't understand this portion, and maybe we don't fully understand these additions, but we don't have to worry about that because we're just looking at these guys themselves. There's no additions involved with other pieces of the algebra. And none of the material that's in these other sections of the algebra even matter to us yet. So what are we looking at? So let's start with, let's see, we're going to start with the notion that we have two vectors, A and B. We definitely know that we can add A and B together, right? So we can definitely add A plus B, and we still are inside this space, right? And because of that, we can take the metric from this space and we can apply the metric to A plus B if we want. We can also take the geometric product of A and B with itself, right? So A and B, A plus B is a vector in the space, and so A plus B times A plus V is also it is now subject to that contraction rule, right? This has to equal eta A plus B, A plus B. Because remember, A plus B, A and B are both vectors in M13, so A plus B is a vector in M13. So I'm basically taking the space-time product of a vector with itself, and this is the rule, right? This is the rule for doing that. So now I can kind of look at the left side and the right side of this separately. Everything's linear, so the next step is pretty darn obvious. We write this as A squared plus AB plus BA plus B squared, right? So that's definitely the left-hand side. And you can already kind of see the inklings of the symmetric part of the product. Because remember what we had over here. I erased it. But the symmetric part was AB plus BA over 2. So you clearly see that that's showing up already in our expansion, in our very linear expansion of this space-time product. Now, both sides of this are linear because that operator over there is linear. So this becomes eta A plus eta A B plus eta B A plus eta B B, right? And we know that eta AA and eta AB, we know that eta being the Minkowski metric as it is, we know that this is symmetric, right? This is symmetric. The Minkowski metric is anti-symmetric. In fact, all metrics relevant to general relativity and relevant to special relativity, at least the elementary versions, are symmetric metrics. So we can combine these two, and we would get eta AA plus eta BB plus 2 eta AB. And then we immediately can do some cancellation, right? Because eta AA and eta BB is B squared and A squared by definition, by the axiom that we apply to the four vectors, right? The axiom, I keep referring to it because it's so important, this contraction axiom, right? There it is, eta AA. And so that leaves us with this. Alpha, the space-time product of A with B plus the space-time product of B with A is twice the Minkowski contraction of the two vectors A and B. And just dividing by 2, we now get the symmetric part of the space-time product AB. The symmetric part is this, equals the contraction between the two, and that is written in shorthand as A dot B, right? That's the shorthand version of this. And that completes the demonstration that they're alluding to right here, right? They're alluding to this demonstration. So it's the last equivalence follows from the contraction relation. That's this equivalence here, right? The key equivalence that they're interested in making sure we understand is that the symmetric part of the product is equal to this Minkowski contraction. So this dot product it's the same as this symmetric piece. So that means now if we go back one little step and we look at AB and we realize that it's equal to this dot product plus this wedge product, and we now know that this dot product part is the symmetric piece. Well, what's left? The only thing left, this wedge product, this must equal the anti-symmetric piece, because this accounts for the entire symmetric piece. Here, the dot product accounts for the entire symmetric piece. You need to get to AB, so all that you have left is the anti-symmetric piece. And so this anti-symmetric piece is identified as the wedge product. And it's really interesting because we know this is a scalar, right? We know this piece is a scalar. And this is not a scalar. This wedge product, as we're going to see, is not a scalar. So this product cannot be a scalar either. Now, if it was just A, it would be a scalar. So there's some weird product out there that when you take the space-time product with itself, this weird space-time product is when you take a vector's space-time product with itself, you get a pure scalar and the anti-symmetric part goes away. But when you take it with any other vector, you get a scalar piece and a non-scalar piece. So you've got this product that produces things that are mixed character. There's a little scalar and a little not scalar. And so that's what we need to get into next, right? And sure enough, the next thing they talk about is, well, what is the anti-symmetric part of this product? Now, you'll notice that we did this proof here without any reference to basis vectors, which means we never really selected a particular reference frame. And we when we write the metric like this, that's very abstract. That's true in every single reference frame, because eta AB in reference frame 1 is equal to eta A prime B prime in reference frame 2, as long as you do the transformation correctly, right? So we can write this. This is in full generality. No reference frame was chosen here to make this calculation a little bit easier, right? And in this particular case, this non-reference frame version of the proof was actually pretty easy. But there is a version of this proof that does in fact use a reference frame, and I want to show you that now before we go, because we're going to be doing a lot of proofs, and sometimes we will in fact discover that it's actually easier to do the proof if we sort of establish a reference frame and then come to understand that we could have done that proof in any reference frame, as opposed to starting a proof like this where we never even discuss reference frames, right? So let's have a look at that other method. Okay, so the first thing we need to do is establish a basis. So we're going to establish some basis vectors. Now, for this purpose, I'm still going to use the E0, E1, E2, and E3. So we are now calling this the basis vectors of this this subspace of our overall space-time algebra. And I haven't really gone into the Dirac stuff yet. We'll probably take that up we'll probably take it up as soon as the authors do. So we have these four basis vectors. Now we're going to assert a couple things, right? We're going to assert that they're orthonormal, which basically means we can make some statements about the Minkowski inner product or the Minkowski contraction of these basis vectors with each other and with themselves. With themselves, E0 gives you, I think in this one it's +1. And EIJ, where I and J can go from 1, 2 to 3. Whenever you have these Roman subscripts, it's 1, 2, 3. If you had a Greek subscripts, it would go from 0, 1, 2, and 3, right? So EIJ, we want this delta function here, but we need the minus sign, so it's -1. So anytime you see a basis vector contracted with itself, if it's orthogonal, then these are actually orthonormal. They're going to be unit vectors as well. Yeah, so they're orthonormal because they're unit vectors, but they're clearly orthogonal. I and J have to be the same. That's a weird little J, isn't it? Let me clean up that J a bit. I guess for completeness, A to E0 with any of the three spatial, the time-like unit vector with any of the spatial unit vectors is also 0. So it's essentially a diagonal metric, right? So this is what we mean when we say we're picking a basis. We pick a set of basis vectors, and we fully understand how the metric operates on those basis vectors. And we're free to choose this kind of basis, right? Basis that has nice Cartesian orthogonal basis vectors, but non-Euclidean. We're using this as Minkowski-ish. So once we've done that, now we can say, well, these are vectors, right? These are four vectors in this thing, so all of these axioms apply. So we can immediately write down what is the space-time product of E, say, mu with E nu, right? And the rule is that it has a symmetric and anti-symmetric part, right? So the symmetric part we already know is E mu dot E nu, which, just as a reminder, is eta mu, eta E mu eta E nu, plus this anti-symmetric part, which I'm just going to write down as E mu E nu minus E nu E mu over 2, right? Because we've already shown that this is the symmetric part and this is the anti-symmetric part. But we also know that this is going to be 0 whenever mu and nu are not equal, right? And it's going to equal either plus or minus 1 when mu and nu are in fact equal. But when mu and nu are in fact equal, this term goes away, right? Because if mu and nu is equal, you get something minus itself. For example, you might get, E0, E0 minus E0, E0, right? So what's interesting here is because of the basis we've chosen, this part is, if mu and nu are the same, everything in this space-time product of these two basis vectors
lives here, and this part, the anti-symmetric part, goes away. On the other hand, if the basis vectors are different, right, then this is driven to zero and this part goes away, and the space-time product between two different unit vectors has to live entirely over here, right, in the anti-symmetric part. Okay, so those are a few of the lessons we've learned about how these basis vectors work in the space-time algebra, given that we choose this metric relationship. Actually, this would apply to any metric relationship, right? This point here about the symmetry and the anti-symmetry is completely general. Okay, so with that in mind, let's have a look at breaking down one of our rules in terms of basis vectors. So we're going to look at this sum of AB plus BA. And what we do is we assert straight up that A is A mu E mu, and B is B nu E nu. And once we've done that, we've chosen our basis, and we're using E, the basis, to be the one we just discussed. So we can create this symmetric product, the symmetric part of the product AB. Remember, this is twice the symmetric part of the spacetime product AB. And we just write it out. We just blow it up, right? The real numbers can pop out in front, and you're left with the spacetime products of these unit vectors. And then we pull out these two real parts right up front, right? So we get A mu B nu, E mu E nu, E nu E mu. And these are space-time products now. So you look, we just put the vectors right next to each other. These are space-time products of unit vectors. And I can blow this sum up into all the parts where the space-time vectors are the same in this, where the unit vectors are the same in the space-time product, and where they're all different in the space-time product, right? And I think I'm missing a factor of 2 here, right? I think there needs to be, right, a factor of 2, because what happens is if mu is 1 and nu is 1, I get E11 and E11. So these two add up to give me a 2. So there's a 2 here. So there's a 2 times this. And so I get this section here and this section here. The problem is on this section here, I know that mu and nu are different. I know that they're different. And because I know that they're different, I go back to what I just did, and I showed that, well, if they're different, we know that the symmetric part goes away, because the symmetric part is equal to the symmetric part is equal to the inner product, which we've established as being Minkowski. So if they're different, this part goes away. So everything that's left is the anti-symmetric product. So I know that the space-time product between two of our basis vectors, when they are not the same basis vector, is in fact just the anti-symmetric part of that space-time product. It's these two things. So, but the key idea is that the symmetric part is 0, right? That we know that, I should just to be clear, write that down. We know that E mu, E nu plus E nu E mu over 2, that must equal 0 for this case. And that's exactly what we have here, right? We have this symmetric piece sitting in front of us. So we know that that symmetric piece equals 0. Okay, so what does that leave us with? Well, that leaves us with, we take this down and we write AB plus BA. We take this 2 out and we put it underneath. I'm glad I saw that too. This is now gone, and it equals, and then this part here, that, this equals 1. -1, this equals -1, and this equals -1, right? So we end up with A0B0 minus A1B1 minus A2B2 minus A3B3, which of course equals eta AB. That's exactly the definition of this whole thing. So we've now shown that the symmetric part of the we've sort of re-verified through using the basis vectors. We've re-verified that this in fact equals this. Now I feel like there's a certain amount of, well, this is what we mean by when we say we're going to throw down basis vectors. We take these geometric or space-time products and we cast them in terms of basis vectors, and then we, knowing how the Minkowski metric works on the basis vectors, we simplify things and we come up with expressions for the components that are something that we're familiar with. So this is just another approach of handling that, of handling that demonstration. Now, admittedly, having gone through this, I sold this in beginning as an alternative way of showing that the symmetric product equals the Minkowski contraction, but that's not really true. I sold that as saying, oh, we're going to use basis vectors instead of total generality. But take note that when we did this, I'm pretty sure that right here, when I wrote out this part, I derived that fact from our original proof, our basis vector free proof. So I think in this particular case, you really do have to start from the fundamentals in order to make this connection, right? Because making this connection was what was so critical. Being able to say that the symmetric part was, so what I did was, in order to say that the symmetric part was in fact the dot product, right? I used this proof, but then I applied that right here to say that, oh, the symmetric part of this is 0, therefore it's just the anti-symmetric part. And then I used the fact that the symmetric part was 0 to eliminate this piece, which of course led to the conclusion that I essentially had already assumed. So this isn't this is just an alternative way of understanding it and a good introduction on how to throw basis vectors into the problem, use the simplifications afforded by the Minkowski metric to sort of see how things flush out. But this isn't really an alternate proof. There are circumstances, however, where casting things in terms of easy to understand basis vectors do make proofs a lot simpler, and I hope to give you a few examples of those as we move forward. Okay, so that takes care of, what does it take care of? It takes care of, let's see, we looked at, we're kind of unpacking this story, and we unpacked it by breaking down, what did we do? We broke down this product exactly as they asked and made this conclusion that the symmetric part was in fact the classic dot product using the Minkowski metric. So we validated this statement, which is, and the next part is to understand this second piece, this wedge product piece, which is obviously the anti-symmetric part of the product. And we'll start getting into that next time.